question time, or coffee time, or maybe pub time for that. So thank you. It's a pleasure. Some of you will know I spent the 1970s in Cambridge, so it's always fun to come home and looking at the changes. What shall I talk about? As you've all noticed, there's a wide range of topics at this workshop, and my attempt to categorize the talks is, one strain is you just have some particular probability model of a random graph, and you study its properties as a mathematician. A more vague idea is, well, you're actually interested in some data coming from the real world, which you're modeling as a graph, so implicitly nature is giving us something which we may or may not know about, and we're trying to do some statistical estimation or do some algorithm on this. My talk's somewhere between, so I'm imagining out there in the real world is something which we're trying to understand, something with a network structure, and we can't observe it exactly. So we have some fuzzy, some noisy data about a network, and rather than attempting to just say what exactly is the network, we're actually interested in some number, some statistic of the network, some number associated with it, which tells us something about the real world. So the issue is, there's a very vague, big area of imperfectly observed networks, which is of this style. People have done this in many different ways, and some of which are being talked about here. So yesterday we had Peter Orban's mention for sampling ideas. So one way if there's a very large network is you just sort of sample a vertex and look at its neighborhood, and you do this a bunch of times, and you've got to make some inferences about the whole network from sampling pieces of it. Later on, there's a area of, I guess, algorithms called link prediction, which basically says that, well, kind of the only thing which is uncertain is that we may have sort of not seen some edges, and so you're trying to use the pattern of edges you've seen to try and predict which of the unseen edges are actually there. So again, there are many ways of doing it. I'm doing it in a particular way, again, where there's a sort of arbitrary true graph we can't see, but we're making a probability model for how what we do see depends on what the true graph is. And that's slightly different. I'm not claiming it's useful for data. It's just interesting as math. So I have many rants, some of which my breakfast mates engaged me in attempting to give some rants. But, number 17, when we make a math model of a real-world network, we tend to do this as a graph. And this is weird, because almost every interesting real-world network is much better thought of as a edge-weighted graph. I won't go to examples, but you tell me you tell me your favorite 100 real-world networks, and I bet that 95 of them are better thought of as edge-weighted graphs. I think the reason people don't do this as a default is that the actual interpretation of the weights is very different. If you think about max flow min cut world, then the interpretation of weight is a flow capacity. If you think about your traveling salesman problem, then the interpretation of the edge weights is a length or a cost. So in that world, being close, the entities you're modeling as vertices, two vertices, being close in the TSP world means they have a small edge weight. I'm looking at the sort of third interpretation, where an edge weight is strength of association. So typically you think of social networks. So you have the Facebook social network of friends, which is sort of this 0-1 relationship. You're either a friend or not. But it's more realistic, if you're trying to get more data, it'd be more realistic to think of strength of friendship. And in this case, we think of, if you're a close friend, you have a stronger strength of relationship. So now this interpretation of having a high weight or a low weight tends to be how close you are in some abstract sense. So again, I say of these 100 real-world networks, I'm guessing wildly that 15 of them, I love to make up numbers here. I claim come up with 100 real-world networks, about 15 of them, the notion of edge is some relationship, and there's some natural notion of how strength you are. I mean, co-authorship network. Instead of just putting a 1, if you have some joint papers with somebody, why not actually put down the number of joint papers? This is not rocket science somehow. Okay, so strength of association might mean different things. I'm kind of going down to specializing more to a friend's idea. I'm sorry, because I'm less organized than I should be because of my breakfast friends engaging me in rants, so it's all their fault here. So I remembered what my slides actually say here one at a time. So of course, in our imperfectly observed network story, it's reasonable to say that if there's a stronger association, that should be easier to observe. So we want to take that into account in our model of what we observe. And so the way I'm going to do it is to say that strength of association means frequency of interaction. You're friends with people because you interact with them in some way. So the edge weight I'm interpreting as frequency of interaction. And to make a probability model, I then say that each pair of people interact at random times, the times for Poisson process, but the parameter is this sort of arbitrary weight on the edge connecting them. And we're now saying this is what we observe. So this is basically our model. There's a set of vertices we can think of as people. They interact pairwise. What we observe over an interval of length time t is the sort of number of interactions each pair has had. And again, I'm saying that the same thing in several ways here. So summarizing the math setup finally, network is a finite edge-weighted graph. There's some statistic, formally a functional on the set of such graphs, some statistic we're interested in knowing. We're interested in knowing the statistic of the true graph, which we can't observe. But what we observe is this sort of fuzzy graph, an observed graph. We watch this for time t, and we see this Poisson with mean t times edge weight, number of interactions. So of course, if we did this forever, the law of large numbers would tell us what the edge weights are, and we'd know everything about the graph. But the issue really is sort of how long do we have to observe this process until we can estimate things accurately? What makes this interesting is that there are two trivially equivalent, but sort of logically different ways of representing our data. So after I've watched this for a while, one thing I could do is say, well, I've observed 3 interactions between the 2 people on the top. So how do I represent those 3 interactions I've observed? Well, I'm drawing 3 edges. That's the so I can represent my data as a random multigraph. On the other hand, if I think of, okay, I'm trying to estimate an edge-weighted graph, what's my estimate of the edge weight there? Well, edge weight is the long-run number of interactions per unit time, so the natural, rather fussily call it, the naive frequentist estimator of the weight is just the sort of observed number of interactions per unit time, so I can say, well, what I've observed is an estimated edge weight of 3 over t at time t, and so I can represent my data as this sort of random edge-weighted graph. So these are trivially equivalent, but they sort of suggest different things. So that's our general problem. We now have a model, so we have a model of what we observed. So the specific model for how the observations depend on the true network, but we want to make no assumptions about the true network whatsoever. So, general comments. Well, this is kind of an overlay project. I mean, anything you do with networks, kind of implicitly assuming the network is known, you can sort of go up and say, well, what if it's not known in this way? Again, we can always do the naive frequentist estimator. That is, we can look at our estimated edge weights and plug that into the statistic we're trying to calculate, but ask a statistician if you have some highly nonlinear function of a bunch of parameters, then one way you could estimate that is to estimate the parameters and apply your highly nonlinear function, but there's no reason whatsoever to think that that's an optimal way of doing things. It just isn't, and you can easily make up artificial counterexamples where it's a very bad thing to do. Conversely, we all also have naive Bayes estimators. The most naive is just a sort of improper flat prior on each edge weight. That's kind of silly, but it actually works. Again, you have sort of a quite different set of problems with frequentist and Bayesian estimators. Interestingly, for many cases, they kind of err in opposite directions, so you kind of can often be reasonably confident that the true value is somewhere between a frequentist estimator and a Bayesian estimator. The final thing, those of us in statistics departments are engaging with data science. the first question being, what on earth is data science? But it's some mixture of statistics and algorithms, and somehow the different viewpoints come up here. That is, ultimately, we're thinking of very large graphs and estimating things. Algorithms people think of cost as computational complexity, how long does it take to find communities, etc. I'm not doing that. I'm thinking computation is free. I'm taking the statistical view that the cost is the cost of getting the data, the observation time. So every 10 years there's a census, and the actual effort in making a census isn't in crunching the numbers you've got, it's sort of getting the numbers in the first place. So I mean the computation is free statistical idea. So the point is that any estimator, and I'm kind of using this naive frequentist estimator just to avoid notation for some other estimator, any estimator, you run it for fixed t, and how accurate it is, that just depends on both t and what the true graph is, and we don't want to make assumptions about the true graph. So to actually make a sort of interesting and sort of sensible, as well as sort of mathematically elegant formulation, a specific formulation is this. So we're in this setting, given the statistic for networks, I want to define both a stopping rule and an estimator. So eventually I'm going to output some estimate based on what we've observed, but instead of saying in advance how long I'm going to observe the process, I have a rule that tells me, well, now I've got enough data, I can output an estimator, and of course this has to be a universal rule that doesn't depend on knowing what the unknown graph is. So that's my project. I'm repeating the project. I should say it's ongoing joint work with a graduate student, Alicia Lee. The bottom line is, you actually have no idea how to do this for most interesting things you'd like to do it. So again, we're trying to do something deep. We're trying to do things uniformly over all graphs here. So we're trying to do something that's intrinsically a bit hard. We can do it for a few statistics which are less interesting or less natural. So what I'm going to say in rest of the talk is basically these three things. That, there are some examples that are easy. So I'll give a typical easy example. I'll say what I think of a key sort of challenge problem in this area is, and then I'll say kind of there's a strange sort of backwards way of looking at this which tells us something. So I want to take a slightly different take on a standard trophic community structure. Loosely, a community is sort of a subset of vertices which is sort of internally better connected than the graph as a whole. And the sort of obvious way of thinking about this in our setting is to say, well, just take an arbitrary subset of vertices A that has some size m, look at the sort of total edge weights within that subset and divide by the possible number of edges. I'm being lazy, I should divide by m choose 2. I'm just dividing by m squared out of laziness here. So this gives me a sort of internal density. So for each m, there's some maximum value of this sort of internal edge density statistic, and I can, so that's now a statistic of the unknown true graph. If I want to estimate this statistic Wm bar true, then I just do the naive thing and think about the same statistic for my observed edge-weighted graph, my observed graph with the observed frequency of interactions. You can readily see intuitively that I'm going to get a sort of larger value in the observed one than in the true one, typically, because I mean there may be lots of maximizing sets, and some of them by chance will have higher densities. So I'm sort of seeing random fluctuations upwards in this context. On the other hand, if you think about how much are these fluctuations, and then sort of reformulate this in a confidence interval statement, it's very straightforward to show, because basically our random variables are sums of Poisson, which are Poisson, we know large deviation estimates, and we just have to start counting things. So one can show in a completely straightforward way here that if we're looking at values of m that are growing as order log n, then we just get this sort of confidence interval for what the true value is in terms of as being slightly less than the observed value. And again, this is, there are explicit bounds I haven't written out, but this is really uniform over all finite edge-weighted graphs here. Now, the kind of bottom line here is what does t actually mean? I mean, a priori we can sort of scale time arbitrarily, so t doesn't quite mean anything very objectively without some standardization. So we want to standardize time so that the number of interactions per vertex per unit time is order 1 on average, and so that gives us an interpretation of time is the number of interactions per individual. I should say again, a similar but more complicated estimator works for statistics like sort of maximum weight matching. Again, if you're an algorithms person, you're used to sort of minimum weight matchings, but that's the kind of the opposite interpretation. You want to match to people who are close to you, and people who are close to you are people who have large edge weights in my story. But basically, it's the same type of thing works for max weight matching, although here the naive estimator doesn't work. You actually have to be clever about how you're going to estimate it, but you don't have to be very clever. But these results said that in order for your estimators to be good for matchings or the previous case, you only need time to be order 1, I mean a large constant. It doesn't depend on the size of the graph whatsoever. And in some sense this is the interesting case to me. Again, if you're trying to apply this type of thing to data, which I'm not claiming is useful, but if you were thinking of applying this, we were imagining you've observed you're some security agency with a 3 or 4 letter acronym, and you're sort of observing metadata on telephones between people, and you're sort of thinking, well, what can I tell if I've observed an average of sort of 24 phone calls per person? What does this tell us about the community structure or something else here? Okay, so again, the sort of paradoxically, the sort of global things we were just talking about tend to be easier in this world than other things. Here's what I think of as the basic problem. The coupon collector's problem tells us that in order for our sort of observed interactions to form a connected graph, we're going to need typically the order log n. We're going to need time log n. We need sort of time to get observations. And the point is that sort of once we've observed that many of interactions, then at least for a sparse graph, we know almost exactly what most of the edge weights are. So in some sense, mathematically it makes sense to talk about connectivity problems, but somehow it's not the interesting case here. So the interesting case is that, again, if you've observed 24 interactions, a multigraph of degree 24, we sort of imagine, in fact, it's going to have some a very large giant component that maybe 99% of the vertices are connected in our observed graph, and moreover, again, typically we think that, again, a subset of the giant component is going to be internally sort of well connected in some vague sense. So the question is, can we make an inference about sort of observed connectivity to the true connectivity? So we'd like to make an inference that if what we see, so I sort of run for a certain time, I want to say conditional on seeing in the observed graph that this kind of intuitively expected, highly connected large component phenomenon, can I infer that the actual unknown true graph has something similar? And this again seems intuitively clear, because intuitively noisiness adding noise is going to make connectivity properties worse rather than better, and this is the direction we want to go in. On the other hand, sort of trying to get a handle of this, I mean, connectivity behaves on sort of extremal quantities, and these are just hard to get hold of in a probabilistic context, so we don't really know how to do it. It's worth saying, nobody actually understands Feshman statistics and confidence intervals, so I'm going to slightly insult you by explaining what we're having to do here, because it's just because I find it counterintuitive myself. So again, in this setting, if we have a theorem that says if the true graph has some property, then I have a probability model for my observed graph, so I can show that with 95% probability the observed graph will have some related property Q. Then the inference, the statistical inference, you learn in Feshman statistics, is the sort of counterfactual way. The inference is that if the observed graph doesn't have property Q, then we can be confident that the true graph doesn't have property Q star. That's fine, but trouble is we want to sort of make inferences in terms of positive things, so we negate everything. And again, this is, if you ever wondered why nobody understands Feshman statistics, this is kind of why. So if you want to make an inference of the form that if our observed graph has a property P, that will make us confident that the true graph has a related property P star, then the theorem we have to prove that goes with that inference statement is the theorem that if if the true graph does not have the property, then with high probability the observed graph doesn't have the property. So the issue is that if I want to prove a statement about connectivity, our first thought from random graph theory is I want to prove my random graph is connected, but no, I have to prove the opposite. So what I have to prove my challenge problem is to say that if the true graph fails some desirable connectivity property, then it's very likely that the observed graph also fails it. And so all this is kind of elementary logic, but it's actually hard to keep in mind when you start thinking about epsilons and delta. At least at my age, it's hard to keep this in mind, maybe not for you. So anyway, that's the sort of background, and this is why people become Bayesians. I mean, because you don't have to deal with this nonsense if you're a Bayesian whatsoever. So I mean, it's you may laugh, but yes, it's so good. You've had an argument for becoming a Bayesian. This is one of it. So here's a backwards way of looking at it, which is kind of cute. Again, the advantage of being a theoretician is that you can sort of change forces in midstream and do it. So I'm going to say this because there's a question for the graph theorists at the end that I want to ask here. So I'm looking at my observation process over an arbitrary graph. I'm seeing this multigraph of observed interactions. One can define a class of stopping times represented by here. I look at the first time that the observed multigraph contains k edge disjoint copies of some object, and the particular objects we'll look at, simple objects of triangles or spanning trees. And here we have a result which gives us a weak concentration of these random variables. Again, everything has to be invariant under time scaling, so it doesn't make sense to talk about expectations without standardizing, but you can standard deviation divided by expectation makes sense. And these are just bounded by numbers, and again, this is uniform over all finite edge-weighted graphs. So this is a sort of universal concentration inequalities here. So somehow we have a technique for proving things like this. So what are we doing here? And of course what this says is that these expectations, expectation of tk for triangles of spanning trees, that's a number that depends on edge-weighted graph. It's a statistic of the edge-weighted graph, and what this is saying precisely is that these are statistics which we can estimate in our desired universal way. So remember that our project was to think about, for a given statistic, can we find an estimator of it where we have a bound like this uniformly, and we're sort of, that's equivalent to saying anytime we have or at least a special case of that is what we're doing here, but we've done it in this backwards way. We sort of come up with a concentrated stopping time, and the fact that we have this type of result is exactly saying that this expectation is some statistic of the graph, which we can estimate by just sort of observing the process once. Of course, we can make them more accurate by just repeating independently a bunch of times and using the square root law. Now, of course, this is weird because these are sort of crazy statistics you never think of doing. So it's not, these aren't, you can think of, if you're wanting a statistic about how many triangles there were in a weighted graph, you use some other statistic, but those are harder to estimate, and these particular ways of doing it with edge disjoint ones it gives us something that we can estimate here. So again, somehow this is about what aspects of our observed graph are sort of concentrated around their expectation. So these results are from a archive preprint. There's a strange general result which somehow doesn't seem to be well known, even though it's almost trivial if you look at it the right way. On Markov processes with some very strong and uncommon monotonicity property, but which happens here. And so basically one can actually start the argument without saying what the objects are. There's a certain part of this argument you can go where you just have, I'm looking at the time until the multigraph contains k edge disjoint objects, and then at some point you have to do a calculation involving the objects, which is entirely trivial in the two cases I can do, but I want to ask graph theorists if they can do the third case. So our setting is, I'm going to say a setting is a game here, and I haven't got all the details, but it's the idea. So we're going to play a little game. I choose a multigraph which has the given property that it contains k of these edge disjoint objects. I'm then going to delete an edge, and then going to give that graph to you. And the question is, can you always find many different ways to restore our property by creating a few new edges? So to do this by example, if I have my k edge disjoint spanning trees, I delete an edge. What am I showing you? Well, I'm showing you this thing where one edge has been deleted, so I've split the vertex set into two. Now you can create edges anywhere. There isn't a sort of constraint on where you can create edges. So what can you do to restore that property? Well, basically you can create any edge from here to here. So you have at least order n edges. You can do this in at least n ways by creating one edge. What about for triangles? Well, okay, I start off with k triangles, so nothing else. I start off with k edges, right, triangles, delete an edge, show that to you. What you see, a broken triangle. How do you get back to the property? Well, you just create a triangle somewhere else on a big graph, and so now you've got to create 3 edges here, but how many you have order n cubed ways of doing it. Okay, this is entirely trivial. But now let's sort of change this. I'm cheating slightly, but I want to change this where my property I'm interested in is being k edge connected. So the question is, thank you. I choose a k-edge connected multigraph. I delete an edge. I give it to you. Is it always possible to do something like this? Is it always possible to add? I want things to be independent of n. They can depend on k. But is it always possible to add some number, 1, 2, 3, or k edges to which will allow us to regain this property? But I want sort of there to be lots of different ways of doing it. And again, so all I know about k-edge connectedness is Menger's theorem, and this doesn't help with us, but so I don't know. There may be some trivial counterexample to this, but or it may be something simple, or it may be some structure theory for k-edge connected graphs. Okay, I'm done. That's it. Thank you.
What do you do if you have a Hamilton cycle? There's just one. I delete an edge. There's a unique way of putting it back. So we have to find a place where it goes. Will you accept it?
Okay. But,
I look at if I'm processing the whole graph, then of course I can put.
Well, right, because the property is containing a Hamiltonian cycle. So the property isn't so just having one. So if and I'm on a complete graph, I mean I can put the edges anywhere. So somehow I can, if you take an edge, I just put in, put in 2 edges to anywhere arbitrarily.
Observation, do you allow?
I mean, it's complicated. There's more stuff I haven't said, but again, the conceptual issue is kind of the way I've said it. The conceptual theory is somehow, I want to know what a k-edge connected graph without one edge looks like structurally, in the same sense in these examples. I know what a sort of spanning tree with one edge deleted looks like, and I sort of know what triangles with one edge deleted look like, and somehow I want to know sort of some structure of this sort of k-edge connected graph with one edge removed, and ultimately I have to sort of do the computation of how long it takes for this recovery process to happen within the probability model, but somehow the first step I need is to just know in principle without any probability what are the possible ways to recover this property. Because I mean, your first thought is again, well, I can tell you, without lots of generality, I tell you which edge I've deleted. Somehow it isn't clear to me that the trick of just throwing in 2 edges works this way. Anyway, okay, this is slightly vague. This is something I haven't probably haven't thought about as much as I should have. Yeah.
There are very few ways of putting back 25 edges to create a Hamilton cycle.
Yeah.
How do you find? That's easily done. You have a big graph, looks quite okay, but still there are only very few ways of putting back 25 edges that will create a Hamilton cycle.
Okay, I haven't thought about Hamiltonian cycles on here. Yeah, right.
Those are nice objects which are easily completed.
Right. Yeah, these are local things. No, I haven't. I don't want to try and think about Hamilton cycles in real time standing up here.
Where is the cutoff?
Okay.
Okay, we have time for maybe one more quick question.
Just, I mean, along in the same vein, I mean, it seems like the most challenging part of the program is to be able to say something about the set of all graphs, and it makes me wonder if extremal graphs are going to come up in interesting ways. I mean, some of them have already been mentioned, and Bela mentioned another one. The other thing is there's this whole literature on property testing, which is comes at this problem from a completely different point of view. But are there interesting deep connections there, or does it not quite seem to be compatible?
Again, I thought about that a little, and somehow, you know, at the bottom of this is a particular probability model. So the calculations we're doing for confidence intervals really depend on the details of the probability model we're looking at. I mean, in the bounds I said, the extremal graph is, you know, the graph with one edge. So the graph with one edge is the worst case here, and at least up to constants, it's the worst case. So again, that maybe says that they are not deep results, of course.
Yeah.
All right, let's thank David. Oh, sorry.
So I do, because what did you mean by many? Because if you've deleted one edge, you can put back two edges in n ways to make it K-connected again. That's not enough.
Again, it's complicated because we then have to figure out the time it takes for our observed process to see that. So the problem with the two edges is that I don't have any control over the I don't have any control over the rate at which I see two edges. The point is I have control over the rate at which I see triangles, because that's T1. So the actual bound, the bound you get out of the idea of creating an entirely new quantity is that you sort of get a bound on how long this takes in terms of T1. And then there's a sort of separate argument that tells you that T1 has to be small compared to Tk. So that, again, things are a bit more complicated than I said here. But somehow just the first step in proving this is to sort of say something which doesn't involve probability, and then you have to figure out how likely it is to happen. Yeah.
Okay. If there are additional questions, maybe we can take them during the break. Let's thank them one more time.